Good evening, one and all. The meeting will be starting shortly. The talks will be starting shortly. Thank you for your patience. Good evening to one and all. Good evening to one and all. Welcome to day 5 of the FDP program. So far, we have seen six lectures from 6 reputed resource persons from both industry as well as from academia. Today, due to some technical issues, Dr. Prashant Sonar is unable to join. So for the first talk, we have Professor S. Nagarajan, Head of the Department and Dean, Academics. He is the professor at Central University of Tamil Nadu. His research interests include developing new materials for organic electronics and understanding how molecular structure alters the properties of such materials. Sir, over to you.
Yeah, very good evening to all of you. Actually, I'm sorry to say that actually the speaker for this session is Dr. Prashant Sonar, my good friend. So I don't know why he has not joined, but he's in Australia now. Maybe because he was in touch with us and also maybe some issue unable to contact him now. So I will be presenting for the next 45 minutes to 1 hour. Then Dr. Hussain will join. And in fact, I will insist to Dr. Sonar to make a presentation tomorrow, right? So sorry for the inconveniences. Because that's one of the main issues whenever we organize things through online. Because if everything is in our hand, it's fine. And person in Australia, maybe it's a late night. It's more than 10 o'clock or plus. And he was with us and he responded very well also. But I don't know, he forgot or whatever it may be. So anyway, so no issues. Anyway, I will be presenting for the next 1 hour. All right. Yeah. Thank you so much for Anu for the introduction. So I'll be going for the slides now. I think my slide is visible.
Yes.
I think it's visible now.
Yes, sir. Yes, sir.
Yeah. Okay. Thank you so much, actually. So I'm going to talk about organic electronic materials. So why? Because you have listened to this fifth day. You have listened to many talks related to. Yesterday, we have a talk from Professor Thomas from IIT Roorkee about OLED. And also from the first day onwards, we listened to a variety of talk. And I know the heterogeneity of the group. Right? Maybe certain things may be difficult for people from engineering background. So my presentation will be very general, and also it will give an idea about why we have to move from conventional inorganic material to organic electronic materials, right? So I'll be stressing that, and also I'll be presenting the kind of materials that are in use, and if time permits, I will showcase some of our work, whatever we are pursuing in Central University of Tamil Nadu, right? And you are well aware that at this stage, right, there are organic compounds. They can be very well used as material for fabricating transistors, like fabricating memory devices, even waveguide, many things are being there, right? So let me have a slide, right? When we talk about materials for electronics, it will come to our mind that, okay, metals are the good conductors. When we say, people will say for electronic industry, people will talk about good conductors, copper, silver, gold, etc. When we talk about insulators, we will be always saying about non-conducting material like plastics, rubber, mica, insulating papers, etc. So if you think about the semiconductors, so from our basic knowledge, it says that yes, we have a silicon, germanium, and those kind of materials are being studied, and it's in our curriculum also. Even we as a faculty, we used to teach the students about the kind of semiconductor like P-type semiconductor, N-type semiconductor. Whenever the holes are conducting, we used to say they are P-type. Whenever electrons are conducting, we used to say N-type semiconducting material. right? And it was initially people were saying that organic materials are carbon-based materials. So they may be non-conducting materials. So nobody was thought of using organic compounds for electronic application. Maybe they were used carbonaceous material as an insulator, not as a conductor or a semiconducting material. So is there what's the scope? When we talk about inorganic materials, we always talk about the conduction band, valence band, and the energy difference between these two. We call it as the band gap. So there are advantages and there are limitations also. For example, one of the main disadvantage with inorganic materials is, right? So if you see that many of these inorganic materials, they are persistent in the environment. It means to say that remain there in the environment. For example, if you have a gadget or some instrument made up of an inorganic the semiconducting material as while fabricating a transistor or whatever it may be. So at the end of the day, right, it has a particular short life. After that particular point, if you're able to recycle it, it is fine. Otherwise, when you are letting into the environment, it poses it will impose toxicity to the flora and fauna, because as you know, these materials are persistent. It means to say they are not being biodegradable. They will not be degraded by the soil microflora or any of the microorganisms. So that is one of the problem. And as you know very well about the toxicity of mercury, lead, and many of these inorganic materials, right? Once it enter into the food chain, then it has its own life. It will be entering, for example, you know about the mercury poisoning in the Japan Sea, right? The mercury entered into fish and it entered into human, and it has been observed that mercury deposits there in the spinal cord and even the bone of people, those who consume the fish from that particular place. So there are these issues. You may pose a question, sir, whether organic materials are non-toxic or not. So from the day one, right, whatever you listen to the talk, so organic materials are right, carbon-based material, right? So when we design a molecular structure, so we can incorporate certain groups, like if you are, for example, if you are incorporating hydroxy groups, like for example, if you take an aromatic system, phenol on biodegradation, phenol undergoes biodegradation, right? Once you have a catechol, you have an 1,2-dihydroxybenzene type, then that molecule will immediately undergo biodegradation by soil microorganism, and it will be consumed by the microorganism, right? It enters into the TCA cycle, etc. So organic chemistry, we have a kind of a system. We can design a molecule to make the molecule soluble in appropriate solvent. We can make the molecule that is that can be biodegradable, etc. Maybe in the other slides I will talk to you. Yeah. So if you think some house problem is there. Yeah, if you think about the growth of Dr. John, can you please block? Yeah. So if you see to that growth of the electronic industry, now we are moving from the microelectronics to nanoelectronics. It means to say that ultimately what we are expecting, we need to have a better performance. As the first speaker of this the FDP program, Dr. Patel, he said that. So we need a better performance. There is a high performance with minimum size. The device to be miniature, and it has to have many functions. For example, he has pointed out mobile phone. So mobile phone, today's mobile phone, right? We are not using radio. Many of us are not going for a dedicated camera, right? So our mobile phone can be solving the purpose of radio. We can capture the images as a camera, and also we can browse internet. Many things are being possible. So how these things are being possible means one of the thing is that technology is growing. We are having a new material. So whatever I'm projecting here is the Moore's law. I think many of you may be knowing about it. So what the Moore's law says that, so the number of transistor count on a microchip doubles every 18 to 24 months. It means to say that the area remains, we are reducing the area and we are going to accommodate more number of transistors. So if you see the graph, the x-axis, we have the years plotted from 1970 to 2010. And in the y-axis, we have a number of transistors, right? You see the number, if you compare 286 system and the number of corresponding transistors versus the Pentium processors. So the number of transistors units are being more. So that's a thing. We are going to accommodate more transistors. So we have to have a good processor. So that is possible means we need to have a new material. So in that case, the organic compounds are one of the main alternative for the inorganic materials, right? So when we talk about organic electronics, organic is a carbon. When we say carbon and related chemistry, when we talk about organic chemistry, it's a chemistry of carbon compounds. So likewise, the organic electronics, it has different names. It is otherwise called carbon electronics or flexible electronics or foldable electronics or plastic electronics, because it has many advantages. Again, I'm quoting the first presentation. So when if the material as organic material, we can make very thin film, we can coat on variety of substrate, make it foldable, flexible, etc. Right? So the like whatever I said about inorganic materials, like inorganic materials, organic materials also we have a semiconducting the organic materials. Again, I'm quoting the previous speakers. So they talk about conducting polymers. So the polyaniline systems, polyacetylene systems were developed in late 90s, right? So they have been proved that organic compounds are also capable of conducting electricity. So like the conduction band and valence band of the inorganic materials, here we have a frontier molecular orbitals, FMO. We used to call it as a frontier molecular orbitals. So one can play with the FMO. That is the highest occupied molecular orbital and lowest unoccupied molecular orbital. One can play with the energy levels of HOMO and LUMO, right? So we can have an appropriate band gap also. So we can engineer a band gap for organic materials. And again, the organic compounds, the processing, right? We cannot use silica as such or the inorganic metal as such. We need to have a high purity material. It needs a very high temperature. And also, the cost involved in it. So for organic compound with a small quantity, we can make the film with of a larger area. So mass production is being possible. And as I said in the previous slide, they are relatively eco-friendly. So we can design the molecule that can undergo biodegradation or a biotransformation, right? And again, a flexibility to adopt the substrate, like a inkjet printer. You can load the solution of a particular organic compound and you can print the circuits by using organic compound. So these days, people are working on solution processing technology that is cheaper, and again, is a widely accepted one. And again, many devices has been demonstrated. People have made transistors fabricated under the ambient conditions. And again, as I said, we can make a very thin film, and overall, if you calculate, the power consumption for the organic material-based devices are being less and compared to the inorganic one. And there are display units if you are going for an organic material that gives more clarity than its counterparts, right? And if you see the quantum of research work published in these. For example, if you look into the graph in the x-axis, it represents the year from 1990 to 2021, and the y-axis shows the number of publications, right? So it shows the potential of this research area. If you see the tremendous growth from 2004-5 onwards, right? The number of publications crossed 1,000, right? From the year I can say from 2016 onwards, more publications are in this area. As I said earlier, there are many dedicated journals for the organic electronics. So the organic electronics is a journal published by elsewhere. And again, the organic semiconductors is another journal published by IOP. And Taylor and Francis, again, they have a dedicated journal. And even IEEE and many journals, even you take any leading or chemistry or physics journals, they have a particular issue or particular article in an issue related to application of organic materials in electronics, either as a a thin film transistor or a waveguide or a memory device, etc. So there is a scope, and again, it's not only in terms of publications. If you see the potential, right? For example, in terms of the research laboratories, there are many research laboratories, not only in the Asian countries, because many laboratories in South Korea, in Taiwan, and if you move to Europe, there are many laboratories in Germany, France, and other countries, and US, Australia. Many groups are working. In India also, selected laboratories are working on mainly the few of the IITs and CUTN, and we are also working on developing new organic materials for electronic applications. And if you think about the funding for this research area, right? So, it's also one of the thrust area for the government of India, and many international agencies. Also, the Ministry of Information and Technology has highlighted organic electronics as a kind of a thrust area for the government of India. So, developing new semiconductors, right? Whatever we today, the FDPs on organic semiconductor. There's so many people are working on developing new organic semiconducting materials. And right, if you think about American Chemical Society, ACS or Wiley, ACS has a dedicated journal on the applied electronic materials. There also you will be finding many articles related to application of organic materials in electronics and advanced the electronic materials, advanced material science. There are many journals, they are publishing articles with application of the organic materials in electronics. So the scope is more. That's why many people are moving. And again, I am saying this area, research area, is a interdisciplinary, or I can say it's a multidisciplinary, because knowledge in organic chemistry is needed. When you want to design a molecule, and to make the molecule, you need to have a hands-on experience to synthesize the molecule. And again, you need to know the principles of spectroscopy and all to characterize the molecule. And later, once you are going for application, automatically, right, you need to have an idea about fabrication of the devices, and also, right, characterization of the devices, right? So that also need to have an idea. And again, whatever you are proposing, at the end of the day, you have to give a mechanism, how the transistor is performing, how this material or how this new organic compound is having a better on-off ratio, or kind of a low threshold voltage or high on-off ratio, that to be supported by the computational tools also. So it is mainly an interdisciplinary, or I can say broadly a multidisciplinary research area, right? So as we know, right, you have been exposed to many devices. Even we can think about if the materials are luminous. And yesterday we had a beautiful talk by Professor Thomas, right? He talked about organic light-emitting diodes. If you see the history of the OLEDs, the people initially, they started with inorganic materials. Mainly people have used rhodium-iridium complexes as a material for the OLED. Now, from iridium, rhodium, or ruthenium, people are moving to organic materials. So there we have a fine-tuning of color is being possible, but there are certain things we have to keep it in mind, right? Material to be thermally, photochemically stable, right? Not only luminescent, it has to have a kind of a property that is to be consistent, right? Then only we can use it for fabricating a device, right? So by using luminescent organic molecules, people have fabricated organic light-emitting diodes and organic solar cells. This also, we listened to the yesterday's talk. So as a harvesting light, as a DSSE or photovoltaic system, people have used variety of organic molecules that are photochemically stable, right? And again, if you think about the field effect transistors, so it has an enormous potential, starting from our smart card to many applications are there for what I can say the field effect transistors, right? So there are many architectures are being available. So whatever I'm presenting here is because you may be interested to note that how the device it looks. So it has a substrate. It may be a silicon wafer or a kind of a material, whatever you are thinking, and over that a dielectric layer. It may be a polymeric layer like a PMMA or other coating. and it's a non-conducting. Then over that, your semiconductor, this whatever this dark yellow color, it represents the organic molecules, right? So the organic molecules can be drop casted, or it can be spin coated, or it can be coated on as a thin film by any other mean. And after that, we can fix the electrodes and connect to the semiconductor parameter analyzer, like whatever we are using ᴑ parameter analyzer to measure the performance of the transistor. Right? There are many architectures. I'm not going to that. And ultimately, the people are working on improving the mobility of the field effect transistor and improving the on-off ratio. That's the ultimate goal. So for that, as engineering people are working on different architectures of the OFETs. As a chemist or a basic science people, we as a chemist, we are working on developing new organic compounds that should have the better performance. So it's right. So as I said, OFETs find application in many fields like sensors, RFID tags, memory devices, health monitoring devices, etc. Right, even the RFID system. Even you might have noticed in your library or the malls now the barcode readers are being replaced by RFID system. And again, people are forecasting, right? Already it is there, right? There are smart textiles to see the body temperature, your sweat, and BP, and all to be monitored by using the organic field effect transistor-based monitoring units. And again, not only like that, it has many application in industrial process, in the defense sector and others, wherever OFET-based sensors are being available. There's another area, organic field effect transistor-based sensors. So there's an area many people are working on it. So for sense different types of gases, starting from flue gas, and again other poisonous gases and other things. So it has a variety of applications. So the OFETs have a lot of scope. And in fact, you can search any of the search engine, like you can go to the Science Direct, you can search the OFET, you'll be finding many research articles, and you can find many patents related to application of OFETs in the field of in any diverse areas. So there again, what I can say, the functional material is an organic compound, right? And see, as I said, so there are we need people are talking about flexible foldable electronics now. So let us think about the paper as a substrate. So this is again right an area. Even a few people in India also working on paper electronics, right? So their substrate is a paper. So over that they are printing this circuit, and again it's a kind of it's a one-time use electronics or throwaway electronics. So as you know, paper has many advantages, right? It is an abundant material, low cost, and paper is biocompatible, biodegradable, and eco-friendly. And people are using simple fabrication methods to print the circuits. And I think you might have witnessed, right, whenever the Christmas greetings or you have a birthday greetings and all. Once you open a greeting card, it will say Happy Birthday or Merry Christmas, right? So there again, the people are, there's if you see it's only a paper or a card. So over that, they have printed the circuit. So there again, organic compound based materials are being extensively used as a semiconducting materials there. So, right. So if you see that there are many research articles, even whatever I am citing is a Chemical Society review published in the year 2015, right? So it is a review mean to say that it's a collection of articles. So many people have extensively worked on paper-based flexible supercapacitors based on paper substrates. So there is a area, many people are working on it. So it's a collection of, if you look into this particular article, you will be finding how people have used as a paper as a substrate for fabricating a flexible supercapacitors. And again, if you see that the organic transistors by using the organic molecules, the low voltage organic transistors, this is published in there is organic electronics in 2015, right? Likewise, right, people are fixing chip, right? People are fixing the transistor-based chips on the currency node. to import the additional security features, right? If you see that this is also published in Advanced Materials in 2011. If you see that the blue color, whatever I am highlighting or showing the pointer, so here again the semiconducting material is an organic semiconducting material, right? So likewise, if you see the material used for, there are many organic materials are being used. There is one paper people have published with pentacene based semiconductor. Pentacene is 5 benzene rings are being connected. So it is a very good P-type semiconducting material, and a lot of report has been reported, and many times it has a better performance than the silicon, right? So simple pentacene and doped pentacene has been established as one of the remarkable material for the organic electronics, right? So again, they have given the characteristics of the transistor, whatever they have used. And I think now you may be interested to note that how an organic material, now I have given an outline. Yeah. So like inorganic materials, we can also think about organic materials for electronics, right? So I talk about the conduction band and valence band in inorganic materials. So with respect to the organic molecules, we talk about the HOMO and LUMO levels. They are called as the frontier molecular orbitals. So by incorporating appropriate groups, one can play with the energy gap between the HOMO and LUMO, right? So these organic semiconducting materials are also classified into P-type, N-type, and P-N-type. This is a P-channel material or P-type semiconductors. Both the terminology people are being using it. So if you see that P-type semiconducting material, when we talk about the physics people used, when holes are conducting, it is called P-type material. So here we used to say if the material is able to give electron. So when it can give an electron, if it has a higher HOMO level, then it can give an electron. So the higher HOMO level is there, means it can easily give electron. So what kind of materials can easily give electron? If the material is rich in electron, or if the material is capable of giving electron, right? As a basic chemistry knowledge says, the amines are basic. Amines used to give electron. We cannot use all bases are as the P-type semiconducting material. There are here I have cited triphenylamine is a kind of a moderately basic amine. Because of many advantages, people are extensively using TPA and triarylamine as a P-type semiconducting material. And as I mentioned in the previous slide, pentacene is a 5 benzene ring with extensive electronic cloud, and it's the pysene is also related to pysene, the pentacene. They are electron-rich molecule. They can give electron very easily. So they can also they can be classified as a P-type semiconducting material. When we talk about N-type semiconducting material or N-channel materials, so mainly electron accepting. So when an organic molecule will accept electron, we need to have a low LUMO value. The lowest unoccupied molecular orbital means it can easily it can accept the electron. So usually the compounds with more electron withdrawing group or electronic accepting group are considered as an N-type semiconducting material. I'll give the structure in the next slide. So here the main problem is there are plenty of organic the P-type semiconducting materials are being available, but the N-type semiconducting materials are being limited. So the reason being the N-type semiconducting materials, as I said, they have a low LUMO value. They can easily undergo the air oxidation, or they can undergo other transformation. So again, there is a demand for the stable, the N-type semiconducting materials, right? And the third category is bipolar or ambipolar semiconductors, right? So here you can make the bipolar semiconducting material in two different ways. You can mix the P-type and N-type together. You can make a PN junction, or one can have a material. So one part of the molecule can give electron as a donor, another part can accept electron. So that is also possible, right? So those kind of materials are called ambipolar. So it has a donating part and accepting part. So it's a PN. It may be a kind of a composite mixing two different compounds, or it can be in a single molecule. One part will donate, other part will accept, right? if you see that the examples, whatever I'm presenting here, if you see the p-type material, we have pentacene as it has an extensive electron, right? Highly conjugated molecule. So it can give electron. Likewise, tetracene, triphenylamine, cornene, piscine, carbosol. So these compounds are electron rich and they can give electron easily. They are classified as a p-type. The same pentacene, if I am replacing all the hydrogens with fluorine, it is called as a perfluoropentacene, right? We have replaced all the hydrogen. See that all the carbon with hydrogen, we have replaced the hydrogen by fluorine. So as you know that fluorine is having higher electronegativity, so what will happen? Is a minus I or electron withdrawing groups. It can withdraw the electron from the aromatic core. So the electron donating capacity of the pentacene is being lost. So because of the presence of fluorine, now it is going to accept the electron. So one can modulate or one can change the p-type material into an n-type semiconducting material. So that's the main advantage with respect to organic electronics, right? You can design a molecule, or I can say you can tune the molecular structure based on your necessity, right? Likewise, the other molecules are the PTCD is a peroline tetracarboxylic acid diimide, NH. The H can be replaced. We can put alkyl groups, making an because this compound is having very low solubility. The solubility can be improved by functionalizing the imide NH with an alkyl chain, so that will make the molecule soluble in common organic solvents like naphthyl. Like this, the peroline diimide, we have a naphthyl diimides. So these compounds are having electron accepting capacity. They are being extensively used as a p-type, n-type semiconducting material. So we talk about the OLED. Yesterday, professor has given a talk about organic light emitting diodes, right? Then we talk about OFETs, organic field effect transistors. So these days we combining OLED and OFET, the OLED and OFET. People have made a material. People have made a device, OFET, organic. The OFET and OLED, they form an OLED, organic light emitting transistor. It means to say it will perform as a OLED light emitting diode, and also it will function as a transistor. So you can that kind of a flexibility is being available with organic chemistry, right? And again, what I said, the PN or ambipolar transistors, the semiconducting materials. For example, as I said, naphthyl imide is an electron accepting part. So other part is giving electrons. So the one part of the molecule is giving as a donor, other part is being an acceptor. We have a very strong nitrile groups are here. It can be a very good acceptor, and this is a donor. So it can very well behave as a PN type of a semiconducting material. So as I said, we can design the molecule to have a kind of an appropriate band gap, to have an appropriate solubility. So that kind of flexibility is being available with organic semiconducting materials, right? So one such molecule is, we worked extensively on triphenylamine and its derivatives. So it is not only organic semiconducting materials. So the polymers, organic polymers, right? Organic polymers are also extensively used in the semiconductor industry. Likewise, here also we have electron materials with compounds or polymers with electron donating capacity. They have been classified as a p-type semiconductors. And again, the material with whatever we have seen, the naphthyl imides, right? So they are with the electron accepting. So they are called as an n-type semiconducting material. So not only simple organic compounds, even polymeric organic compounds are also used as semiconducting materials. So there are advantages with respect to polymers. There are disadvantages also, right? So because one of the problem with polymer synthesis is controlling the molecular weight. So that is one of the issue. Maybe the molecular weight, we will say that it will be in this range. Whereas with small simple molecules, we will be having a particular molecule. Right, so here we'll be having a range of polymers. We will be having a compound with a different molecular weights. Right, a range is being there. So ultimately, the property may not be uniform. Right, that's one of the problem. And also another problem is making a crystalline film with the polymeric materials. That is also a little bit there is also a disadvantage with the polymers. But there are advantages with polymeric material. As you know, polymers are having adhesive binding capacities. So with the substrate, it will very well bind. But organic molecules, we have to find some binding agents, or we have to adopt some other technology to make the material to bind with the substrate, as well as the contact, that is electrode, to be perfectly fixed on the organic material. So both have advantages and disadvantages. So here in this slide, I am giving a kind of appendix. This is a 5-benzene ring containing system, right? Functionalized with the triisopropyl TIPS unit. So TIPS is it has many advantages. So here, with respect to these molecules, usually to impose solubility, right? If you think about pentacene, 5-benzene ring containing system, pentacene is not soluble in common organic solvents. If you want to have a impose solubility on the pentacene system, we have to add appropriate groups to make it soluble in the common organic solvents. So one such strategy is by incorporating the triisopropyl groups, and also maybe to reduce the reactivity. Otherwise, pentacene is not chemically stable, right? I will give reasons in the subsequent slides. To prevent or to block the chemical reactivity, the TIPS, this kind of blocking groups are being used. They will sterically block the reactivity of this middle benzene ring. So here the purpose of this slide is, right, we have a structure, kind of a 5 hexagons are being here. We have a nitrogen at different positions, and in the last two structures, we have an electron accepting group, chlorine, as well as a strong nitro group. So by changing the structure, what is being observed, the LUMO, that is the front-air molecular orbitals levels are being changed. That can be very well observed in the absorption spectrum. The same 4 molecules, they have reported the UV visible spectrum. If you see that symbol molecule, the R represents the TIPS, whatever projected in the previous slide. So you see that absorption maximum for this compound is around 675 nanometers, whereas if we think about the nitro group containing molecule, so it is coming around 850. So ultimately, by changing the structure, so the point here is, so one can play with the molecular structure, and one can move from here. It is what is happening from is a near a region. It shifted to a longer wavelength. So it means to say the property of the molecule is being changed by incorporating certain groups. So the sky is the limit as an organic chemist. So we can play with the carbon skeleton, and your imagination is the end. Whatever kind of a material you want, you can design and you can synthesize. That is we have to make a synthetic strategy to make the compound, right? And you may be asking, right, what kind of compounds can be used? So there are many organic compounds. Can we use all these organic compounds for electronic application? It is not like that. We cannot use everything, right? So there are certain criteria it has to fulfill. So one of the system is, right, once we talk about molecules, as you know, molecules are very, very small. They are beyond nano. Molecules are usually small. Organic molecules are in the angstrom scale, 10 to the power minus 10 meters. They're very small. So the molecule to be connected, the charge has to move from one end of the molecule to another end of the molecule. It means to say that highly conjugated. Conjugated means alternate double bond, right? If a charge is moving from one end of the molecule to another end of the molecule, means we need to have a alternate double bond. Then only charge will move. So one of the prerequisites is the charge has to move, so it to be conjugated in nature. For example, whatever I have given as a pentacene, if you look into the structure, there we have an alternate double bond. I think you have studied about benzene. Benzene is having a conjugated double bond. If you connect another benzene, it will become an naphthalene. If you connect one more, it becomes an anthracene. In all these cases, we have a highly conjugated system, right? So conjugation is one of the important things. And another thing is the thin film structural properties. So we need to have a kind of a crystalline, and also, right, the molecule has to, so thin film is nothing but is an assembly of an organic molecule, right? You are going to form a thin film, means the layer of the organic molecules you are going to have. it has to form a thin film, an uniform thin film. So actually, the molecule will be forming a thin film through a process called self-assembly. So, right, the self-assembly means, if you see the literal meaning, it's an assembly of molecule on its own. So it means that the real definition is not like that. It has to the assembly of the molecule through non-covalent bonded interactions. So, for example, like if you want to move a charge from like if you want to connect to one wire with another, we will be making a joint, or we will be soldering, right? So that the connectivity will be there. With respect to molecules, the molecules are very small, as I said, 10 to the power minus 10 meters. So it is not possible for us to physically connect one molecule with another molecule, or we cannot solder a molecule with another molecule, right? So for that, we are exploiting a property called molecular self-assembly. So self-assembly is a unique property of a molecule, right? The self-assembly is a unique property of a molecule. It means to say that a particular molecule will assemble in a particular pattern, right, under the particular conditions. It means to say the one molecule will be connected with another molecule, right? There will be an array of organic molecules. You'll have a pattern of organic molecules, right? So each molecule is being connected through non-covalent bonded interactions, like the hydrogen bonding, the ion dipole interactions, not through covalent bonds, through non-covalent bonded interactions like van der Waals forces, so that the charge will be moving from one molecule to another molecule. So we have to make a molecule that to be having a conjugated, and also the molecule has to form a good thin film. How thin film it has to form? It has to form a very good self-assembly molecule. It has to form a network of an organic molecule. So one molecule to be connected to the another molecule through molecular self-assembly. And beyond that, molecule, the compound to be pure, right? If it is not so, for each batch of the production, you will have a different performance. Molecule to be chemically purity, materials to be stable. So it's a very, very important thing. One of the question usually people will ask, say, organic molecules many of the organic molecules will undergo the photochemical reactions. It may undergo photochemical reaction, or it may undergo photodegradation, right? So the material or molecule, whatever you are making it to be photochemically stable and it to be thermally stable. There's every possibility that if you're using an organic molecule for a device fabrication, under that particular temperature, if it is melting and if it is undergoing some chemical reaction, then it will not be fit for the electronic application. So material to be chemically stable, thermally stable, photochemically stable. So these kind of stability it has to satisfy. So that's why when we make an organic molecule, we used to test for thermal stability, how long the material will be stable, right? And purity can be ascertained by using spectroscopic techniques, right? And again, ultimately, right, we can play with the band gap. That is also there. It depends upon your application. You can play with the molecular structure to have an appropriate band gap, right? And so if you want to impose a solubility, if you want to have a solubility in polar solvents, you can have a molecular structure with the polar backbone. And while these are some of the critical factors, material to have a long-term stability, as I said, it has to pack perfect, molecular packing to be there, and the energy alignment, so that the band gap and other things to be taken care, right? And whatever, it has to have a self-assembly, it has to have the connected, very good connectivity through conjugation, and again, a good molecular packing, etc. And when we talk about the molecular electronics or organic electronics, so initial days, the people thought that because the polyaromatic molecules, there is a starting from benzene is an aromatic molecule, then naphthalene, anthracene, then tetracene, pentacene. So all these molecules are being considered as acenes. They are because the tetracene, pentacene. If you have 6 benzene rings together, it is called hexacene. So they are generally called acene family. So these compounds are like, if you look into the graphene structure, likewise they have these molecules are fully aromatic. They have a benzenoid skeleton, right? So people initially thought that these materials are being highly conjugated system, and they have a kind of a charge can very well, it can move, right? So they have and people have developed a new synthetic methodology, because if you see the availability of these acids up to the benzene, naphthalene, and anthracene are available as from the crude oil or other fractions. Whereas the other part, from tetracene or pentacene, we have to synthesize in the laboratory or by using some pyrolysis technique. We have to have a kind of a tetracene or pentacene, right? So, so people thought that these kind of the polyacenes will have a good applications. So they developed a new synthetic methodology to synthesize these molecules. And the question is, what about their solubility and stability? As I said, the solubility of pentacene is not at all soluble in common organic solvent unless otherwise. If we functionalize with some alkyl group or some other group, it will be soluble. Otherwise, it is not soluble in common organic solvents. So we have to have anchor certain groups to import solubility, and also if you want to have a kind of a self-assembling property, so we have to have anchor certain functionalities or some groups on the aromatic core to make it soluble, make it self-assemble, etc. Right? So, as I said, the smallest members, they are obtained, the people have obtained from petroleum fractions, and the tetracene and others people have to synthesize. So, as I said, it has been theoretically, people have, based on theoretical calculations, people said that people proposed that the tetracene, pentacene, and other molecules, the conjugated polyaromatic system, they can very well behave as the p-type semiconducting materials. So that prompted the organic chemist, okay, to make a synthetic strategy to make a synthetic scheme or protocol to synthesize these polyaromatic systems. And that's why, based on their input, people have started synthesizing the many organic, the polyaromatic compounds. But they observed that these compounds are not stable. Even if you think about pentacene or tetracene or hexacene, they are not chemically, they are not stable, right? So theoretically, people have said these materials are good for electronic application, but once people have tried to synthesize this molecule, they suffered, because once the molecules are not stable, then automatically the synthesis will be difficult, right? If it is not stable, then how to synthesize? Because they are unstable. They are reactive, right? They are reactive with molecular oxygen. They undergo dimerization, etc., etc. So it is very tough to synthesize. So then later, why these molecules are being less stable? So that has been explained by the class. This is a very basic organic chemistry, right? Because if you see that we used to put 3 double bonds in the first benzene ring, because to have a kind of a conjugation with respect to naphthalene, and the second ring we'll put 2 double bond. With anthracene, first ring will have 3. It means to say it has a 6 set of electron. So the next ring we have 2 double bond. Likewise, it will be. So what the Clark has said that the stability of the molecule has been reduced once you have a more number of these aromatic rings. So what he proposed as the aromaticity is nothing but it is not the odor. Aroma means, don't think that it is an odor. Its aromaticity is nothing but extra stability gained by certain molecules. It is not only applicable to the benzenoid molecules. There are many non-benzenoid aromatic molecules also. So remember, aromaticity is nothing but an extra stability gained by certain molecules. So here what is happening? So this they have a first ring is having 3 double bond. So the aromaticity, the stability is being shared among the rings. So greater the number of rings, the molecule will be gets destabilized more, right? Because this aromaticity is nothing but extra stability gained by the molecule. And what is happening here, the stability or the aromaticity is being shared among the molecule. So that makes the molecule less stable, or I can say more reactive, right? So, right, for example, if you see that people have proposed, they made a high quality, they offer devices made from thin films of pentacene. It has said typically show hole mobilities greater than 1.5 centimeters square, which is higher than the hydrogenated amorphous silicon. But it has an inherent problem. So if you expose to air, it will undergo undergo a chemical reaction. So we have to make a device. Yeah, you can use it, but you have to make a system or fabricate in such a way that to prevent its chemical reactivity, right? So you may be interested to note that what kind of reactivity pentacene or the tetracene will undergo. So like a pentacene, there is another molecule called rubrine. Rubrine is one of the very important molecule for organic electronics. It is nothing but it is a tetracene. Like pentacene, we have 5 benzene rings. Tetracene, we have 4 benzene rings are being arranged. What is happening? It has 4 number of phenyl. Tetraphenyl substituted tetracene is called as a rubrine. So okay, so the rubrine has a whole mobility is about 8 centimeters square. So the highest mobility people have reported, right? So there are combination of pentacene with the C60, many things people have demonstrated, and people have extensively used for. There are many research papers with pentacene. If you see that, many research papers with the rubrine and many devices with the rubrine, etc. Right? So you may be interested to note that what will happen. As I said, tetracene, right? Once you flash light on tetracene molecule, it will undergo dimerization, right? If you are exposed to light, it will form a dimer. And if you heat it again, it will go back to a tetracene molecule. So it's a process. So can we use this molecule for a fabricating device? No. If you expose light, you will be losing the property, right? Because whatever we have studied is a tetracene. And if you expose to light, if your device with the tetracene, if you expose to light, so the material is undergoing a dimerization, so we cannot use it. So that's why the tetraphenyl. So whatever I am saying, that rubrine is nothing but tetraphenyl substituted. So if you substituted a tetraphenyl, the dimerization is being prevented, and that material is showing an excellent property. So we have a tetracene is first reported photochromic molecule. So photochromic molecule, it's reactive in solution. It dimerizes upon irradiation to a colorless butterfly dimer. It's a colorless butterfly dimer. And the retrocycloaddition can be induced by heating. Reverse reaction is called retrocycloaddition. It gives a tetracene molecule. Like the tetracene, even pentacene molecule also, whatever I said. So the pentacene molecule also, right? The aromaticity is once the terminal ring is having 3 double bonds. Others we have only 2 double bond in conjugation. So aromaticity is being shared. So what will happen in presence of the molecular oxygen? It forms an endoperoxide. It forms an endoperoxide. So what is happening? Why this endoperoxide is stable than pentacene means the terminal rings have a sextet. It has 3 double bond. It has a 3 double bond. So this material, endoperoxide, is being more stable than pentacene. You may pose a question, sir, can we use the endoperoxide, pentacene endoperoxide for the application? But you see that conductivity, the alternate double bond is missing here, so we cannot use it. And again, other issues also, right? So we have to think about the molecular stability, the compound's reactivity, etc. So like whatever people have theoretically predicted, so for experimentally it is not happening, right? So because the molecule is susceptible for chemical reaction, it is undergoing a transformation, it is forming an endoperoxide. So these kind of compounds are synthesizing in the laboratory is tough. And again, once you use it in a form of in the device, again, so if it is not stable, again, you cannot get a property. So today it will be
which has some physical limitations like abundance, that availability, downscaling the size, high power requirement, hazardous impact on their degradation in the environment, that is generating huge amount of UAS. Now, why downscaling is important? Now we are interested in devices with increasing computing power and packing density, that is decreasing dimension or size. You know, we are familiar with Moore's law. The co-founder of Intel stated long back in 65 that the number of transistors that can be packed into a given unit of space will roughly double every 2 years. That is, computer power tend to approximately double every 2 years. Okay, everything was, you see, when he stated this statement long back in 60s, everything was going good. That is, shrinkage of the device was going well, and also that means the storage density was also increasing, computation power speed also increasing. But in 2012 or 13, sometimes like that, Murray himself commented that there is maybe a saturation, and I see Murray's law dying here in the next decade or so, because how small we can achieve, because maybe around 10 to 12, 14 nanometer already achieved individual transistor or basic building blocks of electronic gadget size achieved. But this man, in 2016, Brian, he was the CEO of Intel, informed that in my 34 years with the semiconductor industry, I have witnessed several times there was doubt that Murray's law will die down. That means it's not be possible to go further lower dimensions. But due to the development of nanotechnology, due to development of molecular electronics, due to development of organic electronics, and as a whole, maybe due to enormous development of material science, still we approach to our lower dimensions. And nowadays, this Intel and other people, they are using individual transistor size of the order of, say, 14, 15 nanometer, something like that. If you see this cartoon, you see the device size, how it's decreasing. Long back, maybe in 1940s, 50s, we are using vacuum electronics. We are familiar with vacuum diode, vacuum. This is called valve electronics. This transistor bulb, diode bulb, something like that. Individual, this component was having size of the order of meter. Then with the invention of semiconductor, solid state electronics was evolved, and the size of this transistor, then diode, etc., come down of the order of, say, milli, 10 to the minus 3, something like that. Then IC come up, that is microelectronics, then VLSI, and individual transistor as well as basic building blocks of the electronics come down to micro order. And now we are aiming towards molecular electronics, where individual molecule will act as the basic building blocks of the electronic circuits. And you will find that in the internet, there are so many reports where single molecule rectifier, single molecular wire, this kind of things are already reported. Okay. If you see in this cartoon, you see the size of the transistor, how it's going down, and now we are here. Say individual transistor size, the basic building blocks of our computer processor is of the order of 15 nanometer. Okay. And in this cartoon, if you see the calculations speed per second, it's also increasing with the decrease of the individual device size. You see the speed, processor speed also increasing, and now we are here. You see maybe 10 to the power, say around 11, 12 number of calculations per second, and this is comparable with the mouse of brain. But people are aiming to achieve, to go further, and people are aiming to, say, reach maybe even higher speed, 10 to the power 14, 15, 16, something like it, compared to human brain. And people are trying to mimic human brain activity through artificial circuitry. Okay. So as the Murray's law approaches its physical limits, silicon IC face challenges in scaling, energy efficiency, memory limitations, because quantum tunneling effects become effective in silicon transistor at lower dimensions. When gate length is gradually reduced, maybe of the order of 10 nanometer or something like that, even during the off state of the transistor, carriers can easily tunnel from the source to drain. So this will result some kind of leakage current and also result some kind of power dissipation or power consumptions. Also, if the gate length is below 10 nanometer, tunneling occurs due to high speed of the electrons, that is due to the ballistic electrons. Ballistic electrons means electrons whose mean free path is much larger than the medium dimensions. That means if the mean free path of the electrons within the system, maybe within the device, is higher than say device size, maybe 10 nanometer or 10 or 20 nanometer, then there is high probability of tunneling. Okay, so accordingly leakage current, accordingly higher power consumption. Okay, so therefore silicon transistor leaks current when they are below a certain size, which causes their efficiency to fall. This can make the energy consumption of the chip unacceptable. Accordingly, alternative technology or materials are required. So here, resistive switching may play important role, because resistive switching, unlike that of electrons, they are working based on the change of resistance states. So this problem, downscaling, can be easily overcome using resistive switching. Another issue is non-degradability of silicon. Silicon is highly non-degradable material, and if we see that nowadays the average lifespan of a laptop is 3 to 4 years. Mobile phone maybe 2 to 3 years, or even maybe less. And some electronic toys, our kids, they play maybe few days, less than a month or maybe week, and then they throw. Hardly there is any proper disposal mechanism is there. So e-waste is a growing challenge. And here the information is that we are generating huge amount of e-waste, and it's say in 2021 52 metric ton, and it will become say more than 2.5 times in near future. Okay, even UNO also concerned about this e-waste, because the amount of e-waste we are generating is growing day by day. Say growth rate is 38%, but very hardly this e-waste are recycled. This is a big issue, and even UNO sustainable goal, there is one important concern regarding this. Okay, so therefore we need alternative of silicon based memory which can deal with the ever-growing enormous amount of data, and at the same time can minimize the e-waste issue. Okay, here this resistive switching again come forward, because resistive switching can be achieved, or this kind of device can be designed using variety of material, including biomaterial also or degradable material also. Okay, so if one use resistive switching devices, design resistive switching devices using biomaterial or degradable material, so e-waste issue can be resolved. At the same time, the important feature of resistive switching like low cost, easy fabrication, downscaling, flexibility, high data retention, etc., can also be beneficial. Okay, so biomemory or resistive switching using biomolecule or biodegradable material, maybe natural plant material also, may be a very good sustainable solution towards the e-waste problem which silicon is having. Okay, another issue, this von Neumann bottleneck problem. The von Neumann bottleneck is a limitation in the throughput of our normal or present day computer architecture system, where data transfer between CPU and memory is having some kind of problem, because in the present architecture, data storage and processing unit is separate. So data has to flow from the storage place to the processing, then again go back to the memory unit for storage. Okay, so even if you increase the processing speed, then this transportation of data through bus may affect the speeds. So it's like just for understanding, it's like bottle kind of thing. Even if you have a large amount of say some material within the bottle, but the amount coming out, it depends on the neck, size of the neck. Okay, So this is one problem, and in the present computer architecture system, this can be overcome through in-memory computing, where the control unit, that is CPU, and memory may be within the same unit, same memory place. Okay, and here computation will be done within the memory, and this will eliminate the data movement between processor and memory. So it will resolve the energy intensive and time consuming data movement between memory and CPU. So it will increase the speed as well as the overall efficiency of calculations. Okay. So resistive switching memory is a promising candidate for in-memory computing architecture due to its high bit density. That means lower scaling, then compatibility with CMOS process, and non-volatility. So this may be a good alternative to overcome this von Neumann problem. Another issue, brain-inspired computing. In the earlier slide, I have shown that we are trying to achieve, people are trying to achieve very high speed, computation speed, and trying to reach the level where, which is equivalent with the human brain computation speeds. So brain-inspired computing is a emerging research field that aims to create AI, artificial intelligence systems, by mimicking the brain's information processing mechanism. It is also known as neuromorphic computing. And resistive switching device is a very good platform to design this kind of neuromorphic devices. In our brain, we know that the neuron is the basic building of blocks, and the signal communications within our brain from one neuron to another neuron, conduction occur through some kind of maybe ions or some conduction channels. So maybe there are some joints between different neurons. This is known as synapse here, and the neuron sending the signal is known as presynaptic neuron, and the neuron which receiving the signal is known as postsynaptic neuron. So resistive switching memory, in this cartoon you can see that can have an architecture which is mimicking this design, where you see this is an electrode and this is also an electrode in between your suitable material or information storage system. So you can say that this will send the data and this will receive the data after processing. Okay, so this is some kind of mimicking or of this thing artificially. So RRAM can be used to mimic this kind of device, and people are designing different devices to mimic or different functionality. Let us take an example, mimicking learning forgetting process. In our day-to-day activity, if we want to memorize something, what we do? We go on repeatedly reading the same thing. So with the increase in the number of reading, our memorizations also go on increasing. And at certain level, we memorize fully the thing. Okay, so here also it's possible to design a device using resistive switching, where under suitable conditions you apply a pulse at the same place, go on applying, say, first pulse, second pulse, third pulse, fourth pulse, something like that, and you see at the same time, with time or number of pulses, you see the current is increasing. This is known as something like potentiation or memorizing. Okay, memorization. Okay, so and you see it's increasing, and then after certain times it becomes memorizations. Okay, so we can say that maximum memorizations done. Okay, similarly, the reverse process also possible. Again, with suitable pulse applying continuously, and one can erase the data. That is, one can forget the data. You see, and it's a repetition of, you see, a number of pulse, initially increasing the amount of current, so saturation comes, then again erasing, that means forgetting. So this kind of device, it's a mimic of our neural system, which can perform the learning forgetting process very similar to our brain functionality. Okay, so resistive switching can be employed to design brain inspired computing. This is also very interesting or importance of resistive switching devices. If you see in this cartoon, you see that number of papers being published in different areas of resistive switching is increasing with time. So this gives an idea that people are concentrating on different areas of resistive switching. Even in India also, several research groups, several institutes, people are working in this emerging area. The convener of this program, Professor Nagarajan, also doing very good works in this area, resistive switching memory devices. Okay. So device structure of resistive switching memory is very simple. So it's a, you see, suitable material layer fused in between two electrodes. So it's a very simple structure. Bottom electrodes, then you have your suitable material, then again electrodes. Okay, so it's also possible to have two different kind of materials, say first organic material layer, second, maybe third, something like that. Then maybe say nanoair or channel in between the organics, or maybe say nanoparticle kind of thing, maybe polymer kind of thing. So it's possible to fuse or design resistive switching devices using a variety of material. Okay, people are also doing, okay, and playing. And then you apply proper bias, you see again your resistance state from high resistance to low resistance, it's changing. Okay, so based on this IB card, because in resistive switching, when we apply bias across the device, we see that resistance state changes. Okay, and then when we withdraw the bias or apply reverse bias, sometimes it can remember the previous resistance states also. Okay, so based on this IV curve, that means relation between resistance change with applied bias, there are different types of resistive switching. One is broad area volatile resistive switching, another is non-volatile resistive switching. So volatile means you apply bias, you remove the bias, so it cannot retain the resistance states which was switched. Say it is in high resistance state, you apply the bias, it go to low resistance state, but if you remove the bias, it again come back. It cannot retain the states. Similarly, other resistive switchings are non-volatile. That means if you apply bias, your system switches from high resistance to low resistance, then you remove the bias, and still the system can remember or can retain the resistance states. So this is non-volatile. And depending on the nature of the curves, within the non-volatile, there are again different types like unipolar resistive switching, bipolar resistive switching, WRM, write once, read many type of resistive switching, then complementary resistive switching, and each and every type of resistive switching has their different kinds of applications. Okay, so this is a threshold switching. Okay, so here you apply bias, say 0 to plus volt. Okay, so initially system is at high resistance state. At certain bias, it switches from high resistance to low resistance. Okay, conducting states. We say this is set. That means it's changes its resistance states. And normally, this resistive memory, the data or information are stored in terms of resistance states. Maybe if HRS is say 0 state, then LRS is 1 state or high state, something like that. So when we switches, we can say that a 1 is set on the memory. So it's a set. Okay. So during scanning, it switches from high resistance to low resistance. Okay. Then again, if we apply reverse bias, say plus volt to 0, this direction, you see some bias range, it can retain the informations that is high conducting, low resistance state. Then suddenly again it go back. That means it resets to its high resistance state. Same thing happen at the opposite polarity also. Negative bias, it sets to low resistance state. Then again opposite bias minus V to say 0, it again reset to 0. So this is known as threshold switching. It again has different types of application, like it can be used to solve sneak path problem, then synaptic device, selector device in memory, etc. Then under non-volatile switching, there are write ones, read many kind of memory or resistive switching. So here, when we apply bias, say 0 to plus V. So initially the system is at high resistance state. At certain bias, the device changes its resistance from high resistance state to low resistance state. So that means it sets from HRS to LRS, or it sets from 0 to 1 state. Okay. Then if you apply the opposite bias, that is plus B to 0, you see it follow this line. That means it is in high conducting states, it behaves as a conductor, follow Ohm's law, something like that. Then again 0 to minus B, still it's, you see, it's linear. So even if you remove the bias, still, and after sometimes if you apply some say pulse or something like this, say here, you will see that current of the order of here. Okay, so that means once it switches from high resistance state to low resistance states, it's retain or hold the states. So we can it is told write once. That means you can write applying the bias at this voltage to 1. That means you can write once 1, then it will retain the 1 for longer time. This is just like ROM memory. So here you can read the information again and again. Okay, so it's like ROM. So write once, read many. Okay, so it has applications where you need information to be stored for longer time. Okay, permanent storage, etc. Okay, so this is ROM memory. Then the next one is unipolar resistive switching device. Okay, so here you apply bias, say 0 to plus volt. Okay, and you see that your device switches, say here, this is set voltage to high conducting, low resistance states. Okay, so you apply some compliance, that means limits the amount of current flow through the device. Compliance means you will set or program in such a way that your device across the device the current flow will be under certain value, or you will limit the current flow across the device. Okay, so if you limit the current flow optimize this, you will see that it will say switch or set from high resistance to low resistance state at this point. Then if you apply reverse bias, you will see that it will retain. That means it will maintain the high conducting state. Okay. Same thing happen for here also. Now, if you want to erase, that is when reset, remove the data, then what you have to do? Again, you have to apply 0 to plus volt, okay, without compliance. Then it will, here you see it resets. That means again it moves or come back to its high resistance state, okay. So here one can say that set, that means writing one, that is changing the resistance state from high resistance to low resistance, and then erasing, that means changing the device resistance state from low resistance to high resistance, done in the same polarity. Okay, that's why its name is unipolar resistive switching device. Okay, once the data is written, you can read somewhere here. You can choose proper, say, read voltage before set. Okay, so that you can read. This is common for all the devices. Okay. Then bipolar resistive switching. Here it's unlike that of unipolar. In unipolar, you can have set reset operation in same polarity, but here it is in two different polarity. This set reset occur. So here we apply say 0 to plus volt initially, then at set point or set voltage, it switches from high resistance to low resistance. Then if you apply opposite bias, you see it maintain the high conducting or low resistance state. But at particular negative voltage, negative bias, say it's B reset, you see it switches to again low resistance to high resistance state, that is low conducting states. Okay, so here one can say that we are writing once one, then it will maintain the data, then you can erase here. So it's something like RAM kind of thing. Okay, so it's resistive random access memory, it's bipolar resistive switching. So you can write the information, you can erase the information many times. Okay, and for reading, once you have written the information, you can read, say you can choose a proper reading voltage somewhere here less than V set and greater than 0, and you can measure the say current or resistance across the device, and you can check whether this is in high conducting or low conducting states. Okay, so it has a lot of application like memory chip, neuromorphic computation, security, logic applications. So many applications are there. Okay, this is another resistive switching. It's a non-volatile. This is complementary resistive switching devices. Okay, here you see if you apply say voltage, unlike to that of the earlier stages, here we apply say minus volt V to plus V. We apply bias minus V to plus V. So initially it's in high resistance state. Then at certain VTH1 or certain say plus V1 bias, it switches to high conducting low resistance states. Then again it's retain the states for this time period. Then again another say higher voltage, it switches to high resistance states, that is low conducting states. So it retains up to this amount of time the low conducting state. Same thing happen for opposite polarity if you apply plus B to minus B. Unlike to the other earlier cases, we say initially our device is in a high resistance state. So this is something like binary 0. Then at certain bias, our system switches from high resistance to low resistance, which is equivalent to binary 1. But here, the 0 and 1 is not like high resistance or low resistance. Rather, it's a combination of two resistance states. Because here, for example, say if you are applying, say, minus B to plus B. So we measure the resistance state of this region, negative polarity, then positive polarity. Okay, and if you go from this part to this part, plus B to minus B again, we measure the resistance state at positive bias region and negative bias region. So 0 and 1 is a combination of resistance states at both positive bias and negative bias. Say state 1 is low resistance state plus high resistance state. So maybe low resistance state here, then during the same bias, you see high resistance state here. So it's a 1 is low resistance plus high resistance. It's a combination of two states. Similarly, 0 is the opposite. Okay, so it's high resistance state plus low resistance state. So there, in any states, either 0 or 1, there will not be any conduction between two electrodes or across the devices. So it has also some advantage. We will see with some examples later. Okay, because in earlier cases, in one state, our device is always conducting. There is conduction between bottom and top electrodes. But here, in either cases, 0 or 1, hardly there is any conductions. Okay. So when you are going to design resistive switching memory, you have to analyze some performance parameters of your device, say memory window. Okay, so this is the primary criteria of your device to use as a memory. Okay, so this is nothing but the ratio between the high resistance and low resistance, that is two resistance states of the device. Because you are storing your information in terms of resistance, and 1 and 0 are as high resistance and low resistance. Okay, so there should be sufficient distinction between these two states, so that there should not be any superposition of the two states. Okay, so the ratio between resistance of these two states is known as memory window. So when we design resistive switching memory, initially we have to study the memory window, whether the window is sufficient to say that yes, this system can be used as a memory. Okay, then switching speed. This is again very important, because nowadays electronic circuits speed is very important. Okay, so when you design a resistive switching, the switching speed, that means your system switches from high resistance to low resistance, or low resistance to high resistance. So this transition time is very important. So you have to analyze the switching speed also. This is very important. Then stability. You see, whenever you are designing or doing some research, aiming for some application in future, you have to deal with stability of your device. You have to be very concerned, because this is very important. So here we are talking about memory. So you may have to store some information for long time. So your device should be stable in two way. One is your store information, your device should maintain for longer time. Okay, this is one. Another is without much sufficient variation. For example, if you are storing 1 in your device, it should maintain 1 for longer time. Okay, so what we do, we study this thing in two ways. One is we design a device, then may study the characteristics and keep the device in certain conditions and go on measuring with time, maybe daily or maybe once in a week, something like that for several days. Okay, so this is something like to have idea about physical stability of the device with time, whether device is stable or not. And when you store the information, whether your device is stable in terms of retaining the data, this is called data retention time. For example, you have made a, say, ROM WRM device. So you switch your system from high resistance to low resistance state. Now, as per the device configuration, your device will retain the data for longer time. So you have to study how long it can retain. Okay, so you write some information. That means you switch your resistance states, change your resistance state to a desired state, then check how long it can retain the value with acceptable amount of degradation. Because if degradation or variation is crosses certain limits, then it's difficult to use. Okay, it will have problem with data reproducibility also. So data retentions also an important issue. Then device yield. This is also very important because you are designing device. So for real practical applications, you have to check reproducibility is very important. Okay, so one has to check, for example, I have made, say, 100 device. Out of this 100, how many devices show reproducible behavior or characteristics, performance? This is very important. So if I say design 100 similar devices, identical device, and see that out of this 100, my 80 device show reproducible behavior, we say that this device yield is 80% or something like that. So good device yield also is one important criteria for applications. Okay, then read endurance. Okay, read endurance is number of times you can read your stored information. For example, you have designed a ROM, you have written one information in your device. That means you have changed your resistance state of your device from high resistance to low resistance. Okay, here. Now, as per the device configuration, it will retain the state for longer time. But you have to read the data stored in the memory. So what you have to do, you have to read the data again and again. And this may be done applying a pulse of certain amplitude, optimized amplitude of very small duration at a certain time interval. You have go on applying. So maybe 100 times, 1,000 times, 4,000, 5,000, 10,000, something like that. Go on continuously. Okay, and see how many number of times you can read. Okay, the data stored or this resistance state of your device. This is very important. Okay. Then cyclability. This is also important. Say, for example, bipolar resistive switching. In case of bipolar resistive switching, it's possible to switch the resistance state from high resistance to low resistance. Then again, it's possible to come back to its initial high resistance state. That means one can switch from high resistance to low resistance. That means write a 1, then again switch from low resistance to high resistance. That means can erase the 1 and write again 0. Okay, so this is possible. So one have to check how many cycles one can do this operation. That means writing, then erasing, writing, erasing. So it's a cycle, write, erase cycle. So number of cycle, if you have more, then your memory is showing good performance in terms of application. This is required. Okay. So once you design, we have a memory, then one has to characterize this kind of parameters to have idea about the performance of the memory. Okay. So these are some recent publications on resistive switching memory from our lab, and all the publications are available in our lab website. So if somebody interested can go through the papers. Okay. Now we'll show some of our recent works on resistive switching memory. We recently performed in our lab. We have studied resistive switching using tetra-indolyl derivatives. This molecule is, we are in physics department, so we hardly have enough experience about molecular structure. So mainly our friends from chemistry, they design the molecule, they mainly synthesize the molecule, and we as per our requirement. Okay, so this molecule is synthesized by one of my friend in chemistry departments. So we design a device like, say, this is a schematic of organic molecular layer. Then we deposit the array of upper electrodes using sputtering, and these are golds. And the bottom electrons, ITO on the glass substrate, we purchased this thing. We didn't deposit or design this thing. Okay. So this is the very simple structure. We designed this layer, indole layer, using several techniques. Okay. We followed spin coating technique, then drop cast, then Langmuir-Blodgett technique also. Okay, and different thin film preparation techniques has their advantage as well as disadvantage. So LV technique is very important and unique because this is a ideal technique. One can prepare monomolecular layer in optimized suitable conditions. Okay, the technique is very simple, but of course one has to be very careful and take proper care. Okay, it's something like that. We have seen, say, water plants flowing on ponds. Okay, now if someone, say, try to compress the floating water plant on the pond using a bamboo, then just compressing the area available for the floating plant to float. So what will happen? The area will decrease. So area per molecule will decrease. Your floating plant will come closer. At certain time, each plant will touch with each other. So they will form a continuous layer kind of thing. Okay. Then if somebody further compress, then one plant will go above or some plant will go below bamboo. That means some collapse will be there. So there will be a compact arrangement, optimized arrangement of plants, something like this. So here also suitable material form dissolve in volatile solvent, water insoluble solvent like chloroform or something like that, then spread on water surface within the machine. Time is allowed to evaporate the solvent. Then there are computer control barrier. It will compress and molecule will come closer and make a compact form. Okay. There are different ways to have idea about the system. There are some imaging system, then measuring surface tension also it's possible. Okay. And deposition is also very simple to understand, but very tricky. We are familiar with the cream layer when milk is being heated. If you dip a spoon across the cream and take out, you will see that cream layer will stick on the spoon. Here also same thing done. Suitable substrate, dip across the floating layer, then take out, so layer will stick. So in principle, it's possible to deposit single molecule layer on the substrate under optimized condition. But of course, a lot of ifs and buts are there because it's molecular order dimension. A minute amount of dust is a minute amount of air flow can also change everything. Okay, there are a lot of interactions with the substrates and the floating molecule, maybe van der Waals interactions, ion-ion, so many electrolytic interaction, so many things are there. So one has to optimize. So we designed this device using spin coating LB technique, drop casting also. And we found that each technique has its some contribution to the performance of that device. Okay. So this is the cross-sectional. This is the surface of the device after depositions, and this is the cross-section of the device, cross-sectional same image. This is the LB films, thickness say 80 nanometer or something like that. Sorry. So here we have seen that our device showed bipolar resistive switching. Here you can see. So it switches from high resistance to low resistance state. Then it's retain the states, and again it's reset at particular voltage and go back from low resistance to high resistance. So it's possible in both way. You can set, say, plus 0 to minus B, then set here, then reset. Again, you apply 0 to minus B, reset here. Okay. Or opposite polarity, also 0 to plus B, it's set, then reset. So it's independent of bias polarity, we have found. And we have shown that when the current, we have seen that current across the device crosses 20 milliampere, the device got short circuited due to Joule heating. Here you see, it cannot again come back to its initial states. Okay. So this is the conducting AFM image of the device under different conditions. This is without bias conditions. Near the switching, you can see the spikes due to conduction channel across the device. And this is after on state, you can see that continuous channels are there. Then we optimize different conditions. We optimize the device yield. It's 86%. Memory window is very high, 10 to the power 6. We studied the retention also. Okay. And we analyze the mechanism also. So we are not going details here, but here we have seen that oxidation reduction play an important role in the conductions or changing the states from high resistance to low resistance, then again reset from low resistance to high resistance states. We studied the device behavior by changing the temperature also and measure the temperature coefficient, and we found that gold filament formed between two electrodes. Okay. Then we have seen that this molecule showed bipolar switching, just the earlier example. Here we increase the temperature and expose the molecule at very high temperature, and we have seen that within this temperature range, the nature of switching changes from bipolar to complementary resistive switching. Okay, and sorry, this is very important, complementary switching, because one issue is because when you have bipolar switching, your zero state, your device is at high resistance state, but when it is in on state, your device is at low resistance state. There is conduction between two electrodes. Okay, in real, for practical applications, there are not a single cell because there will be a number of cells in crossbar array. Okay, so say this is a cell, you see these are each cell, so number of cells. Okay, so say this cell is a zero is stored, say this is in high resistance states. Okay, so for reading this state, what you have to do, you have to apply some bias, you say read line or something like that. Then you have to measure the resistance state, that means current across the device. So if it is in zero state, the high resistance, then say if you measure the conductivity from here, it is expected that across this cell, there will be hardly any conductions. But since it's in crossbar array and maybe other cells, say maybe one is written here, one is written here, one is written here, then what will happen when you apply a bias to read, you will see that there, since one is there, that means this device is in low resistance, high conducting state. So current can flow across this, like this channel, and this current can come here. Although you applied bias to read the resistance state here and expect that there will be no current since it is in high resistance, but there will be crosstalk disturbance. This is known as snake path problem. Okay, so this CRS, complementary resistive switching, can overcome this, because unlike to that of bipolar resistive switching, here one state and zero states are combination of two states. Okay, so if you apply say -B to +B, then the resistance state here and here, these two combination may be a say 0. Then resistance state here, that means 1, and here this is 0. So these two may be a 1, or maybe vice versa also. It depends as per your assumption. Okay, so in either case, 1 or 0, hardly there is any conduction, your device conduction between two electrodes, because one part is in high resistance in say case of say 1 state, and in case of 0 state, this part. Okay, so hardly there will be any crosstalk, because all switch or all individual cell will always be in high resistance state as a whole. Okay, though one is written there. So crosstalk or stick path issue can be resolved using this CRS resistive switching. So we have seen that this same indole derivative, when treated up to certain heat or temperature, then its switching behavior changes from bipolar to CRS. Okay, so we again characterize the retention behavior, stability, then endurance, cyclability, everything, and we found that it show very good kind of stability. And here mainly we have seen that from this fitting characteristic, that oxygen vacancy contributes to the conduction channel across the two electrodes. Okay, then again we studied another indole derivatives, and we found that initially it does not show non-volatile switching. It was volatile threshold switching. Okay, but when we mix this molecule with stearic acid in suitable conditions, we found that it forms, or it show WRM, right transient many, okay, kind of behavior. Okay, so these are some morphology of the device. Then this is cross-sectional image, and we have seen that in presence of stearic acid, some pores kind of forms, and we expect that due to this long alkyl chain, this may act as a charge trap. And so once it's form the channel between the two electrodes, it can traps the charge, and the channel remain for longer time. Okay, so again we characterize the device, and we apply a patent, and it's granted using resistive switching using indole derivative. Okay, then we analyze the a rule of functional group on resistive switching. We design this molecule is a imidazole derivatives, and with this long chain with donor, and we mix with stearic acid, and you can see initially it show bipolar resistive switching. Then when we replace this group NH using methyl group, the benzyl group, we see that oxidation reduction across this molecule was not possible. Okay, actually this thing was synthesis was done by our chemistry friends, and I am not much expert in this synthesis, etc. Okay, so when we stop the oxidation reduction across the molecule, we have seen that it's not possible to have the switching. Okay, so here functional group play an important role. Okay, Then we have demonstrated that nanoparticle induced performance enhancement of coumarin based system. Okay, and here we have seen that the memory window, it's a write once read many kind of application memory, and you see that memory window initially it was 10 to the power 2, but when we incorporated ZN nanoparticle, it becomes 10 to the power 3. Device yield increases from 36% to 83%. Read endurance, initially it was possible to read the stored information around say 1270 times, but in presence of ZNO, it's possible to read around 10,000 times. Okay, and retention, the stored informations, we have seen that it can store even more than 10 years. Actually, we did some extra, we measured physically around say 200 days, and then we do some extrapolation and fitting studies, and we showed that it can retain the data without much degradation of the resistance state, even up to 10 years, and which is very good for real practical applications. Okay. Then we designed some biomemristor also using natural biomaterial, protein, etc. Okay, so biomemristor is a memristor where biomaterials are used as an active material, and the main advantage is biomaterials are flexible, degradable, compatible with the environment. This is the main environment. You can play with the scalability of the molecule and hence the device. You can biomemristor are easy to process. You can use natural biomaterial, so you can decrease the cost also. They are environmental friendly, self-degradable. These are the main advantage. There are a lot of promising applications like wearable electronics, biomedicine, artificial intelligence, information storage, etc. Okay, transient electronics. Transient electronics is very important and coming up because there are a lot of applications for like say implantable device or sensor to have idea about the body condition, etc. Because this kind of transient electronics, your device is stable up to certain defined time period. After that, when the requirement of device is over, then device may be dissolved in some eco-friendly solvents. Okay, so they may be used as implantable device also. Okay, so transient electronics are very promising, and we have also demonstrated some transient electronics applications of the resistive switching devices. Okay, so a few of our recent works on biomemristors, we have demonstrated that lysozyme can be used to design write once read many memory, which is non-cytotoxic and also show transient and sustainable electronics applications. Okay, so we designed this device and found that it show ROM characteristics. We analyzed the memory window, then device yield, it's around 74%. Then device stability, it's very interesting. You know, normally biomaterials are less stable, but here we have found that our system is stable. We incorporated clay, natural clay in between the device, and we found that the stability of our device physically, that means experimentally, more than 700 days. Okay, then we extrapolate up to 3,000 days. Still, it was the memory window was good with respect to practical applications. Okay, so this is the device cross-sectional image, same images. This is the stability we have studied. You can see that it's almost reproducible IV curves even after 700 days. Okay, then we extrapolate using MATLAB software, and we have seen that even after 3,000 days, the gap between two resistance state is good enough to read or to distinguish these two resistance states. That means stored informations can be distinguished easily even after 3000 days, which is very good with respect to practical applications. Okay. Then we analyze data retention, cyclability, etc., and transient behavior. We have demonstrated that our device can be dissolved in lukewarm water within a fraction of seconds. In say 10 seconds, you can see we measure the absorption of the device once it's just put in the lukewarm water. After 5 seconds, this blue one. After 10 seconds, you see it's flat. So no, there is no active material, device material. And also we studied the IV curve. You see it's this green, initially the red curve, you see this 2 states was there. But when we dip it in lukewarm water for 10 seconds, then take out, then measure the IV curve, we see that it show linear IV curve. This is due to ITO. Okay, it's conducting, so it's showing coherent nature. Okay, so it's show transient nature. Okay, and also we have exposed our device upon to environmentally derived bacteria. Okay, this S. aureus and ᴑᴘᴘ, and this is important because when you throw out your device in the environment, you have to check there are so many microorganisms. Whether device is, if it is eco-friendly, then it should not harm the microorganism in the environment. So we expose our device in these two bacteria, and we found that hardly there are any effect in the bacterial growth, and it's unaffected. So we can say that our device is non-cytotoxic. So it's not affecting the microorganism in the environment. Okay, so this is very good for environment also. So it can resolve the e-wastage issue also. Then we design memory devices using glutamine sulfate. This is another protein, and we have again demonstrated the write once, read many applications using this glutamine, and we have seen that the device is stable even more than 200 days. We study, but you see, after few hundred days, it's difficult to go on doing experiments because our scholars, students, they need publication for their PhD. So we have to stop and go for publications. Okay, but we analyze, we try to extrapolate and have some idea about the stability also. Okay, so here we have seen that the device is stable even after 10 years. You can see that we apply the extrapolation method, and the device yield was greater than 85%. This is very good in terms of applications also. Okay. Then again, we analyze the transient electronic behavior of the device, and we found that our device show transient behavior. But of course, here the time is little bit more, and we saw that for 100% to 100% dissolve the device in water, it took around say 8 minutes. Then you see the flat line, and we also measure the IV characteristics. We measure the same also, we analyzed. Okay, so as a whole, the glutamine based device, so ROM applications, it's promising for ROM applications with very good data retention behavior, high device yield, and also transient behavior. Okay. Then we mix this glutamine with graphene and found that initially glutamine was showing write once, read many, ROM kind of behavior. But when it's mixed with graphene, we have seen that it show bipolar switching. That means RRAM kind of behavior. Here mainly work function of the our active layer material glutamine affected due to presence of graphene. so conduction also affected. So it show bipolar switching. Okay. Then we design some resistive switching using natural biomaterial, that means plant extracts. So with help from our biology friends, we extracted the plant extract from, this is a very common plant, and it's a water plant, water lily, and from the flower we extracted the plant extracts following standard procedure. Then we make the device, and we analyze the device behavior. And we in one device we incorporated clay. You know, clay is very interesting because clay is a natural nanomaterial. Okay, they are layered structure, and they have colloidal size. They have high cation exchange capacity. That means, and due to layer structure, you can incorporate other material in between the clay layer or incorporate on the clay surface due to cation exchange reactions. So it's a very good material to incorporate or to make hybrid material with organic material. And during organizations, the orientation or organization of the organic material changes. Accordingly, their electric, electronic, and optical behavior changes. We have done a few works on how these organizations of material affected the optoelectronic behavior of organic material incorporated into clay. But here we incorporated clay in the active layer, that means within the plant extract in one case, and we have found that the presence of clay affected the device performance. Okay, so this is the device in absence of clay. So it shows ROM behavior with memory window 10 to the power 2. Device yield was not very good, but it's 55%. Read endurance around 8,000. These are some characteristics of endurance and retention. Yeah, here we incorporated the clay leponite with the extract. And interestingly, you can see that here we see memory window increases several times. Earlier it was 10 to the power 2, but here it's become 10 to the power 4. Device yield also increases from 55% to 88%. Data retentions, it can retain the data even beyond 10 years. In earlier case, it was only 500 seconds. So, and also it's possible to read the stored information more than 10,000 times. So performance increases enormously in presence of clay leponite, and clay itself is a natural material. So hardly it will harm the diversity or generate any e-waste. Okay, so we characterize the system. Then this is another example of water lily. We have demonstrated neural computing applications and try to mimic the potentiation and depression. That means memorizing of our brain functions. Okay, I already given one example during the introduction part that here this neuron transmit from signal from one neuron to another through the junctions between the two neurons known as synapse, and one neuron which sends the signal we say is presynaptic neuron, and the neuron which receives the signal we say is postsynaptic neuron. Okay, so here we formed the resistive switching device using this water lily and leponite with optimized conditions. Then we apply pulse at certain duration continuously at a particular. We have found that the conductivity or current across the device go on increasing, and after certain times it's become saturated or maximum current attained the device. That means we can say that maximum memorization level. Then again at reverse polarity, pulse of suitable width and for suitable duration and amplitude applied, and you see go on increasing the number of pulse, and this you see conduction across the device go on decreasing. So it's something potentiation, that means memorizing, then something reverse process, this is depressions, and we have done these operations continuously a number of cycles. This memorizations, that means potentiation and depression. Okay, so we demonstrated some kind of neuromorphic applications using these systems, and we said that this may be a very good potential material for future neuromorphic systems, and at the same time this is biodegradable also. Okay, then again we designs biodegradable rewritable read-only memory using a commonly available plant whose scientific name is ᴍᴇᴛᴏᴘɪ. Again we extracted the plants and designed the device, studied the device, and we have shown that it's rewritable read-only memory, because here you see once you apply the bias, it's go to high conducting states, it retain the states, but when it crosses 0, then it again go to high resistance state. So within this part, once you store the information within this part, it can retain, even bias is withdrawn. So if you apply a read bolt is somewhere here, you can read again and again. You have written the information, you can read again and again. But if you apply bias from say plus bolt to minus bolt less than this threshold, then it becomes again reaches to high resistance state. That means it forgets its one stored in the system. So it can be used as rewritable. You can rewrite, and at the same time, once you read, write something on the memory, it will retain for some times. Okay, unless you erase it. Okay, it's something like rewritable CD or DVD, something like that. So these are the images, and also we have demonstrated these non-volatile ROM devices using rose petal. Here again plain extract from rose petal and demonstrated its ROM applications. We characterized the device with device yield 80%, and we have got a patent using for this degradable rewritable memory using ᴍᴇᴛᴏᴘɪ. Okay. So in conclusion, we can say that it is possible to design both volatile and non-volatile memory stores based on resistive switching, variety of synthesized as well as natural biomaterials. Maybe plant extract can be employed to design such biomaterials or memory stores. Due to advantages like flexibility, high data retention, downscalability, low cost, as well as low power requirement, resistive switching based memory may be a potential alternative of existing silicon based memory. I was listening in earlier lectures, Professor Nagaraj was mentioning that how chemists can play with the structure of the organic compound to have different functionality. So this is the flexibility. In case of silicon, hardly you can have this thing. So here you have the full flexibility. Biomemory stores may have potential applications towards wearable electronics, implantable electronics, biomedicine, artificial intelligence, neuromorphic computation, etc. So, and also, of course, this can resolve the ever-increasing EWAS issue. So, as a whole, this resistive switching is a very promising alternative for present silicon-based memory in near future. Okay. So, at the end, I would like to acknowledge my group members. They have done this work I have shared with you, Dr. Bapi. Now he is in Forensic University. Dr. Surojit, he is in Osaka. She is my PhD student. Now she is in Taiwan for 6 months. Ritanova and Rahul is still working in the lab. So these are the collaborators related to this work, and this is the funding. So thank you all. Thank you very much for your patience and listening. Okay. So now, if you want to ask something or can discuss or share, you can share. Okay.
Okay, as the sir said, the floor is open for discussion. If any queries, you can either raise the hand or put it in the chat box, sir. Any queries? Okay. Nagarajan sir, any comments?
Yeah, thank you so much, sir, for your excellent presentation. You have given a kind of starting from organic to biomolecules, biological, the isolated natural products, starting from resistive memory to with the different things, with the filamentary conduction and all. Really excellent, and right, it will be. It's in the YouTube also. People are watching in YouTube also. It's I think any questions, John? Yeah,
So for now, I won't put any questions.
the people have appreciated. Yeah,
Thank you, sir.
so in the absence of course, let us thank the professor for sparing his valuable time with us. And really, it's an eye-opener for many of the researchers and those who are pursuing or planning to pursue in this research domain. Yeah, because they see that professor has used the chip the biomaterial to the organic materials with and he has showcased the performance also as materials are with a high performance, with the stability, with high endurance and all. So we really appreciating Professor Syed Arshad Hussain for accepting our invitation and sharing his research with us. Thank you so much, sir. Thank you very much. And yeah, thank you, sir.
Thank you, sir. Thank you. And also thank you for giving me the opportunity to present my work with the audience. Thank you, sir. And hope we will have in touch. Thank you very much.
Please, sir. Thank you so much, sir. Thank you.
Yeah, Anupama, you can wind up the session.
We have come to the end of day 5 of Organic Innovation, Semiconductor Innovations, the FDP program. On behalf of Department of Chemistry, Central University of Tamil Nadu, and ATAL Academy sponsored Organic Semiconductor Innovations, I'd like to thank our guest speaker, Dr. Saeed, for his time and patiently explaining from the basics and for his wonderful talk. Thank you so much, sir. To the participants, please fill your feedback forms for your attendance, and we'll meet again tomorrow at 2 p.m. for the final day of Organic Semiconductor Innovations. Thank you.
Thank you very much, Sir Hussain, sir. Thank you very much.